This video is all about taking a situation that we have angled forces and being able to create net force equations from them. Because there's a little extra thing that we need to add in there when we have force components. So the key to this is stay as organized as you possibly can. So I'm going to use different colors to represent the X and the Y axes, kind of like we did in the first video. So if you are struggling with creating free body diagrams with broken down angled force components like you see up here already, make sure you check out one of the earlier videos that kind of walks through the process to solve for that. So I am going to divide up my sheet into a couple of ways. The first one is I'm going to do my net force equation for all of the X forces, and I'm going to create one for all of the Y forces. Hopefully I can keep the same colored pens for both of those. So for my net force equation, I'm going to say the sum of all the forces in the X direction, or the sum of, or essentially our net force, is equal to, and as I look at my force diagram, I see that going to the right, I'm going to say is positive, going to the left is negative, that the X part of the second tension is going positive. So I'm going to say Ft2x, and I'm going to keep that positive. And Ft1x is going to the left, which we set as negative. So I'm going to say minus Ft1x. But the problem with those force components is they're not actual forces. They're just a way for us to break down angled forces so we can compare them to each other. So what we're going to have to do is use trig identities to solve for that in terms of Ft1. And this is where it gets a little bit tricky. So if I look at my triangle, let's focus on Ft2x, so the x component here, is if I see my angle, which is theta 2, according to theta 2, Ft2x is my adjacent side. So I have my adjacent side is Ft2x. I'm going to write over there. We have our angle, and our hypotenuse is going to be that second tension force. So that's what we want our equation to be in terms of. So I have my adjacent side, which is this guy right here. I have my hypotenuse, which is this guy right here. And so I'm going to look at which trig function that best fits. So since I have adjacent, it looks like it's either cosine or tangent. And since I have hypotenuse, that's going to be cosine. So what I can write is cosine theta equals adjacent, which is Ft2x, over my hypotenuse, which is Ft2. So I'm trying to solve for Ft2x in such a way that will give me Ft2. So if I multiply both sides by Ft2, I'll have Ft2 cosine theta equals Ft2x. So now I can take all of that stuff that I just found and plug it in there. So let's do the same thing for Ft1x. So since we can't have that because it's a force component, I need to have that in terms of my angle here, which is theta 1, and the Ft1. So in a similar way, we have the adjacent side, which is Ft1x, and we have the hypotenuse, which is Ft1. So we can write kind of another equation saying cosine theta, this time we're talking about theta 1, that angle on the left side, is equal to my adjacent side, which is Ft1x, over my hypotenuse, which is Ft1. And just like we did in the earlier part, I'm going to solve for Ft1x. So if I multiply everything by Ft1, I come up with, Ft1 cosine theta equals Ft1x. And I can do the exact same thing as I did down here and plug that in for that guy, since I know what Ft1x is. Okay, so I'm going to take this big fat equation and I'm going to rewrite it down here. So I know that the sum of the forces in the x direction are equal to, since I know what Ft2x is in terms of the tension, I'm going to replace that. So I'm going to say Ft2 times cosine theta. I'm going to keep that minus in here. And since we know what Ft1x is in terms of the hypotenuse, I'm going to plug that in as well. So we're going to say Ft1 cosine theta. And if I'm being specific like I should be, I should probably put my thetas in there since they're talking about different angles. Now, since our object is at rest, we could also say that they are equal to each other. So if we wanted to go a step further, we know that if we have a balanced diagram in terms of the x direction, we can set that to 0, which would make Ft2 cosine theta 2 equal to Ft1 cosine theta 1. So either of these would work out. That bottom one is just a little bit more specific. So we solved for the equation for this. Now we have to do the same thing for the y forces. So let's start with that initial piece where we have the sum of the forces in the y direction is equal to, and if I look up here, we have positive, I'm going to say is up, and negative is going to be down. Ft1y, the y component of that tension force, is going to be positive, so I'm going to say Ft1y. It looks like Ft2y is positive, so I'm going to keep that as positive, and gravity is pulling down, so that is negative in our coordinate system. So I'm going to say Fg. Okay, so now we need to do the same thing and replace our y components in terms of the hypotenuse and the angle. So if I look at this is kind of a different situation. Let's start with that theta 2 just because it's on the right side. We have the opposite side, which is Ft2y. So I'm going to kind of write that over here. Opposite goes Ft2y. And we're given the hypotenuse, which is Ft2. So that's going to show us which trig function we want to use. And since we have opposite and hypotenuse, it looks like sine is going to be the way to go. So if I set my equation up, it's going to be sine theta, in this case theta 2, is equal to the opposite side, which is Ft2y, over the hypotenuse, which is Ft2. And if I want to solve for that value so we can eventually plop it back in, I'm going to multiply both sides by Ft2. So my equation becomes Ft2 sine of theta 2 equals Ft2y. So I can take that and I can plug in, since we know that that's equal to Ft2y. And we can do the exact same thing for Ft1y. So since we're also dealing with the opposite and the hypotenuse, we're going to say sine of theta 1 is equal to the opposite, in this case is Ft1y, over Ft1. And if we multiply both sides by that force of tension, we have Ft1 times sine theta is equal to Ft1y. And I can take all of that and plug it in there. So now let's rewrite that down here. So we have the sum of our forces in the y direction. We plugged in this value, Ft1 sine theta 1, plus, and we plug in this value, Ft2 sine theta 2 minus the force of gravity. So we know that all of the forces in the positive direction have to equal out those in the negative direction. So if we wanted to, we could also show that the force of gravity the forces going down, is equal to ft1 sine theta 1 plus ft2 sine theta 2. And both of those would work out. So this is a problem with a lot of trig in it, but notice the progression that we made of going from the free body diagram. We broke it down into components, created our net force equation, solved for the x and y components in terms of the hypotenuse or the tension forces, and we replaced those with the ones that we solved for.